Okay, recording. Welcome you all to the Brazilian Algebraic Geometry Seminar. So today I will present the speaker, and I have the pleasure to introduce to you one of the organizers of the seminar, Marcos Jardim from the University of Campinas in Brazil. He's going to talk on the classification of codimension 1 distributions of degree 2 on the projective space. So please, Marcos.
Thank you, Eduardo, and thank you everyone for showing up for this presentation. So I'm going to talk about some joint work that dates back to a first paper that I did with Omega Andrade and Mauricio Correa, and then more recently joint work with also with Mauricio Correa and Alain Muniz. And finally, with my student, Hugo Galeano, who is soon to present his PhD thesis. So let me try to make a setup of the problem in a broader framework. So I'll take a smooth projective variety, dimension 3, with a cyclic Picard group. Tx and omega 1 will denote the tangent and cotangent bundles, and I'm going to set this number there, the minimum twist of the cotangent bundle, so that the cotangent bundle has a global section. This number I'm going to call rho x. For instance, this rho is equal to 2 when x is the projective space. Now, if you take a one form, you can think of this this one form is said to be saturated if it's not the multiple of another one form of smaller degree. And this integer d here that I'm putting here is called I'm going to call the degree of the one form, right? So it's what it deviates from the minimum, so to speak. So this is called the degree of the one form. But this one form can be also regarded as a morphism because of this isomorphism here. We can think of this as a morphism from the tangent space to this line bundle. And the image of this will be the twisted ideal sheath for some subscheme, possibly empty, but in principle, some subscheme of dimension at most 1, if the one form is saturated. If I call capital F the kernel of this omega, regarded as a morphism from the tangent bundle to the line bundle, I get a short exact sequence like this. And this short exact sequence is what I call a codimension 1 distribution on X of degree D. This kernel sheath, the capital F, is a reflexive rank 2 sheath. This is called the tangent sheath of the distribution D. And the scheme Z is called a singular scheme. And the singular scheme may not be a pure dimensional scheme. So I can filter out, right? I can take out the maximal zero dimensional subsheath of the structure sheath of the scheme. So that the quotient by this maximal zero dimensional subsheath is the structure sheath of a scheme, and this scheme is going to be of pure dimension 1. So that's what I call a curve, right? So a curve for me is a one-dimensional subscheme of P3, the space curve. And this D here is, as I said, it's called a codimension 1 distribution of degree D, and it's a foliation when the one form here, the omega, satisfies this quality here. And in this case, we say that omega is integrable. Now, there's a relation between the Chern classes of the tangent sheath of the distribution F and the numerical invariance of Z. By the numerical invariance of Z, I'm saying it's the degree of the curve, the Euler characteristic of the curve, and the number, the length of the zero-dimensional, of the maximal zero-dimensional subscheme. So this is the length of that sheath U in the previous, right? So it's basically the degree and the Euler characteristic of this scheme Z. But then the Euler characteristic of Z can be separated into two other invariants, which is the length of this zero-dimensional sheath and the Euler characteristic of this curve C. And then I'm going to define this subset here of the space of saturated one forms. So this set here, I mean the open subset of saturated one forms in this vector space here. And I can break this down according to these numbers, the term classes of the kernel sheath, the second and the third term classes of the kernel sheath. And it turns out that these sets here are moduli schemes. So they are projective. They are actually quasi-projective varieties. And they are moduli schemes in the sense that they represent a certain functor that I call the distributions functor that parameterizes class families of codimension 1 distributions on by threefold X so that the term classes of the kernel sheath are fixed. And that's the same thing as saying that the degree and genus of the degree and Euler characteristics, so to speak, of the singular scheme are also fixed via this relation. And our object of study is are actually these moduli schemes here, these strata. So if there are any questions, please feel free to interrupt me at any time. So now let me try to set up what I call the classification problem. So we have these various strata here of this open subset of this affine space here. And you can characterize these strata either by the term classes of the kernel sheath of omega or the degree and genus of the one-dimensional part of the singular scheme. And the classification problem goes as this. So if you fix a threefold X and an integer G, a degree D, first, can you find out all the values of these pairs, A and B or D and G, that occur in the stratification above? So can you characterize all the possible numerical invariants that appear in this stratification? How many strata are there? And second, can you describe each stratum? Can you give the dimension? Can you tell whether the stratum, whether each strata is irreducible, whether it's rational? And moreover, this is a problem that our friend is highlights. Can you tell the degree of the strata in this projective space here? And remember that there is an open stratum corresponding to the case when the singular scheme is zero-dimensional. In other words, the curve is empty. And these are the so-called generic distributions. So, the distribution is said to be generic if its singular scheme is zero-dimensional. And we observe that these generic distributions are never integrable. So my goal today is to address this classification problem on the projective space, so when X is P3, and the degree is small. So I'm going to talk about degrees 0, 1, and 2 today. First, let me recall that a torsion-free sheath is called mu semistable if every subsheath of G, every subsheath, proper subsheath of G, satisfies this inequality here. So this is the so-called slope of a sheath. And when S is a rank 2 reflexive sheath, and the Picard group of X and Z, which are the hypotheses that we are working with today, right? So the fact that X has dimension 3 means that the kernel sheath will be a rank 2 sheath. And we're also assuming that the Picard rank is Z, then the Picard rank is 1. So it's actually enough to check whether it has no global sections when T is sufficiently large, right? When minus T is smaller than this number here. And the first theorem that I like to mention is that if the tangent, if X has mu semi-stable tangent sheath, then a generic codimension 1 distribution, then the tangent sheath of a generic codimension 1 distribution is also mu semi-stable. Right? So this is a nice result for people like me that enjoys stable sheaths, stable reflexive sheaths. So this is the one general result we can get for whatever for this a large class of threefolds. But from now on, I'm going to focus on P3, and we're going to see that F is actually mu stable in several other cases as well. Right. So the message here is that genetic distributions give you have stable tangent sheaths. Now, how does the classification in degree 0 goes? And this was already known in the late 70s by Jardim. So there are two possibilities only. One possibility is that the tangent sheath splits as this sum of line bundles, zo1 plus O1. And the singular locus is actually a line in P3. And the other possibility is that F is this twisted no correlation bundle, and the singular locus is empty. Right. So this is the only two possibilities for the singular scheme and the tangent sheath. These ones here, so since the singular, saying that the singular locus is empty, saying that these guys are the generic distributions. Right, so these guys are the generic distributions, and they are never integrable, as I mentioned before. This is also an example, right? So we knew from the previous theorem that our the non-correlation model is mu stable. And these are the non-generic distributions. Right? So in this case, there are only two strata, the open strata, and this other one strata here that is actually the Grassmannian of lines in P5. Right? So if you if we go back here, so making x equals P3 and z equals 0, remember that rho is 2 in the when x is P3. This space here is a copy of P5, and the Grassmannian of lines in P3 is a quadric in P5, and this quadric is the closed strata in this stratification here, right? So this stratification, when d equals 0, only has the open strata and the closed strata, and the closed strata is the Grassmannian of lines in P3. So this is the classification of degree 0 distributions on P3. It's, very classical object, and it was known back to already known by Jardim. The classification of degree 1 was already known as well, and I'm going to try to summarize all the information here in this little table. This table was worked out in the paper I mentioned with Omega, Andrade, and Mauricio Correia. So these are the possible values of the second and third chain classes for the tangent sheaths, and the degree and genus of the singular locus. And here is a description of the one-dimensional part of the singular scheme. So the first line here corresponds to the genetic distributions with empty one-dimensional parts. So this second number here, the sig3, actually tells you how many isolated singularities, tells you the length of the zero-dimensional parts of the singular scheme. So for a generic distribution, this is how many isolated singularities you have. So this is 5 here. This first line corresponds to the genetic distributions. And then you have another class of distributions for which the singular scheme is a line plus 2 points. And this family of distributions has dimension 15. This last column here of the dimension of the space of distributions is worked out in very recent preprint joint with Mauricio Correa and Alan Muniz that we posted just last week on the archive. And by the way, doing a little advertisement here, Alan will talk about this work next Friday, this coming Friday, on the online seminar organized by Fernando Kuckerman in Buenos Aires. So I guess Alain will say how we come up with these numbers here. So this third line, the singular scheme is a conic plus 1 point, which may or may not be embedded. And finally, you have this case in which you have a twisted cubic and no points. No isolated points, just a twisted cubic. So in these cases, the first Chern class is always equal to 1. F is stable whenever it does a lot of splits as a sum of line bundles. This is the last case. So in this case here, the tangent sheath splits as a sum of these line bundles. And the integrable distributions, so the foliations, occur in these last two entries here of my table that I put in red. So the so-called rational distributions are contained in the distributions of type 111, right? So this part here. So these are the so-called rational foliations, and the logarithmic foliations are here. This other case. This is only generic, right? So this is not strictly speaking true, I guess. So this is only generic. And these, if you don't know what rational and logarithmic foliations are, never mind. But just that this is the notation for the so-called rational and logarithmic foliations. Not really relevant for my presentation today. And this big table here is the classification of the degree 2 distributions on B3. So this first column here is all the possible Chern classes of the tangent sheaths. Again, I highlighted in red the places where the integrable distributions occur. So these are the Chern classes of the possible Chern classes for the foliations. This third column here gives you the degree and genus of the one-dimensional part of the distributions, so of the singular set of the distributions. And here is a description of the possible singular loci of one forms of degree 2. And the last column here about the dimension of these families, this I haven't finished computing all these numbers. I only put the numbers I know about, and for these numbers that I selected, that I inserted here, I know that the families of distributions are irreducible. For the other families, I still don't know neither whether or not it's irreducible nor its dimension. I don't know yet. So these last two are probably easy to figure out, but then these these ones in the top here are more delicate. I'm not sure how to proceed here. This this middle column here, this is the so-called spectrum of the tangent sheath. The spectrum is a set of discrete numerical invariants of rank 2 reflexive sheath that basically tells you the dimension of some cohomology, some of the space of the cohomology vector spaces. The cohomology of the twisted tangent sheath here. So this is the information that these numbers carry here. What's important for me is that I highlight later on is that not every rank 2 reflexive sheath with these Chern classes occur as tangent sheath of a codimension 1 distribution of degree 2. And this is reflected in this choice of spectrum, right? So a sheath with these Chern classes have several different possible spectra, but the sheaves that appear in the as tangent sheaves of a codimension 1 distributions only have this particular spectrum here, and so on, right? So for some cases, the spectrum is unique. Like this case here, there's only this is the only possible spectrum. But for other cases, there are several other possibilities, and and I give you what possibility does arise in this. So you know, it pretty much tells you what type of reflexive sheaves occur as tangent sheaf of codimension 1 distribution. Right. So this is a big table. I think the most interesting part is this bit here that tells you where one form of degree 2 can vanish, right? So the possible vanishing loss line of a one form of degree 2, and when we encounter something, you know, a double line of genus -2, for instance, which is a non-reducible, non-reduced, and you cannot deform into something reduced as well. You have this guy here is also a double line of genus -1, or a double line of genus -2 plus a line, and so on. You have some interesting curves appearing here in this line. So a bit more information. So the first Chern class of these, the tangent sheaf is always 0 in this case. And the tangent sheaf is always mu semi-stable whenever it does not split as a sum of line bundles, as I mentioned here in the bottom of the table. These two cases are two cases in which the tangent sheaf splits as a sum of line bundles. So whenever it doesn't split as a sum of line bundles is mu semi-stable, and it's properly mu semi-stable. Properly mu semi-stable means that it's mu semi-stable and not stable. So it's properly mu semi-stable only in this case here, 1, 2. All the other cases, we have a stable tangent sheaf. And as I mentioned, not every sheaf with the given invariants, Chern classes, and even the spectrum do occur as the tangent sheaf of a distribution. And also here in the table, I put some ACM curve here just to quickly recall what ACM means. ACM means is the acronym for arithmetically column. And one characterization is this, right? So the ideal sheaf of the curve has no cohomology in level 1. The first cohomology module, so-called round module of the curve, is true. Okay. So I'm more or less halfway through my talk. Feel free to interrupt me if you have any questions. But let me compare this classification of distributions with the well-known classification of codimension 1 foliations of degree 2 that was done by Cerveau and Lins Neto. So they show that there are the quasi-projective variety of codimension 1 foliations of degree 2 have 6 irreducible components that are labeled more or less like this. So these are the rational components and the logarithmic components, and there's something called an exceptional component and a pullback component. So this table here gives you the Chern classes of the tangent sheath for each of these families of this of foliations. The tangent tells you a little bit about the tangent sheath and the degree and genus of the one-dimensional component of the singular locus. And one observation is that these families of foliations are not flat. So the main distinction between the classification that I'm doing here, that's summarized by this big scary table, and this classification of Cerveau and Lins Neto, is that these families, the rational family, the exceptional family, and so on, these are not flat families. So there's not an exact match between this Cerveau and Lins Neto classification and ours, right? So the match that I'm doing here in this table is only generic in some sense, right? And what do I mean by this is that, you know, there are some degenerate rational foliations for which the tangent sheath is actually a split of the sum of line bundles. And so there's not exact match between the two classifications. That's just this sort of generic match. Good. So in comparing the classification of foliations in low degree and the classification of distributions of low degree, I like to point out the following, what I call intriguing observations. The first is that, well, these claims here that I'm making here in these slides, these claims hold up to degree 2. And I have no idea what happens for higher degree. So for degree 2, the kernel sheath either splits as a sum of line bundles or is mu semistable. Or it's mu semistable and not locally free. So these are the two possibilities, either for the tangent sheath of a foliation, either splits as a sum of line bundles or it's not locally free and mu semistable. The other observation is that the second Chern class of this kernel sheath is always bounded by this, right? So degree squared plus 2, this little formula here. Differently from, so if you look at this table here, right? So the second Chern class goes up to 6, but the foliations only go up to second Chern class equals 3. And something similar here. So this is degree 1 now, right? So degree 1, the second Chern class of the non-integrable distributions can go up to 3, but the foliations, the maximum second Chern class is 1. So you know, this is something that caught my attention, right? So it's not unheard of that a geometric condition like integrability imposes topological restrictions. So imposes a tighter, right, a smaller upper bound for the second Chern class of this bundle. Remember, the second Chern class has to do with curvature. Now, a more algebraic observation is this, right? So the first cohomology module of the kernel sheath vanishes. This is something that you do by observation. Here in the classification, and you look what happens for these guys where foliations appear, and then the first cohomology module is trivial in this case that I highlighted in red here. So I think this is an interesting algebraic, wild guess here that this may happen in higher degree as well. And the other observation is that the one-dimensional component of the singular scheme is always a ACM curve, and ACM curves are always connected. So this is like a stronger version of a conjecture posed by Cerveau, right? So Cerveau, in one of his more recent papers, he puts this as a conjecture that the one-dimensional component of the singular scheme of a foliation is always connected. And my observation here is that it's actually arithmetically codim. So these claims hold for up to degree 2, and what about higher D? Right? So I think this is these are one lesson that I took from the classification. Now, halfway through my talk, let me try to explain a little bit how that big scary table is populated. Right? So how do you construct examples, and how do you prove that certain things do not exist? The cheaper way to produce these codimension 1 distributions is uses this Bertini type argument here. So if you take a globally generated rank 2 reflexive sheath, then the dual twisted by 1 occurs as the sheaf of a codimension 1 distribution, and whose degree is equal to the first term class of this G here. And this is applied to stable reflexive sheaves where F twisted by 1, F twisted by 1 is globally generated, when F is a stable reflexive sheaf with these term classes. So for these term classes, you can do this simpler construction here using a Bertini type argument, and you prove that the distributions do exist. Now, the second construction is a bit more elaborated, but let me try to explain how to build up this diagram here in the slide. So the starting point is this morphism here. So if you take a generic morphism, this generic morphism will degenerate along the smooth connected curve C, and you end up with this short exact sequence that I highlighted in red. And so this claim here that for a generic monomorphism, first, why a generic monomorphism exists, why a monomorphism exists, and why the degeneration locus is a smooth connected curve is, essentially a consequence of the Bertini type argument that I mentioned in the previous slides, and the fact that omega 1 twisted by 3 is globally generated. Right. So with this in mind, you make this short exact sequence here. Now the next step is you choose a line that is disjoint from the curve C. And choosing a line is the same as making this diagram here. So this short exact sequence that I put in blue. Right, so we have a morphism from O minus 4, right, given by the two planes. So the line is the intersection of two planes. So the two planes are here. And you get this line. And with these two short exact sequences that I put here in red and blue, you complete this diagram here and construct this sheath G, obtained by the extension of these two ideals. Now, focus on this middle column here. When you twist it, you get something like this. Right? Sorry, not when you twist it, when you dualize. So if you dualize the sequence, you get something like this. And this is the codimension 1 distribution that we are looking for, of degree 2, right? Because what I have here is also degree plus 2, so in this case, degree is 2. So you have this this codimension 1 distribution here, whose standard sheath is this sheath G2. This is our reflexive sheath. And the W, the singular loci, is going to be the line L, this line, plus 14 points in this curve C. So we get, with this construction, we get the, let me go back here to the table, we get this entry of the table, where the singular locus is a line plus 14 points. Okay? Remember, C3 is always the number of isolated singularities. Right? So we get this construction. This is the construction behind this top line here. Okay. And how do I know, the Chern classes of this reflexive sheath here, G dual? Well, because I know the degree and Euler characteristic of this scheme W here. And out of this information, I can figure out what are the Chern classes of G2. Now, there's a general argument behind this previous construction, and I state the proposition there, not really very, relevant, the technical distribution. Just that the starting point, let me just highlight that the starting point is a foliation by curves, so a short exact sequence like this, where I have good control over this scheme Z here. And then I take a non-zero section of this conormal sheath here of the foliation by curves. And out of these 2 bits of information, the foliation by curves, so this short exact sequence and a section of this reflexive sheath here, I can make build that whole diagram in the previous slide and take care of several cases. Right? So this general construction here allows us to tackle these cases here. The case that I pointed out before, which is the 514, and then these other cases here. You just have to be smart and clever about choosing this sequence and choosing the section. Right? So if you are clever about it, you can do it. Okay, so this is the third technique, right? So the third way to construct examples. There's a fourth construction, which is described in this slide. Note that, let me perhaps go back here to so maybe this is enough. So what I want to do is construct a sequence like this. So another way to construct a sequence like this is show that you have morphisms. So if you are given a sheath, show that you have an injective map, right? So a monomorphism from the given sheath to the tangent bundle, whose co-kernel is a torsion-free sheath. Right. So the challenge here is this. So given a sheath, show that you have a monomorphism whose co-kernel is torsion-free. And this third technique to do these constructions goes precisely along, along these lines. So give you a criteria on how to prove the existence of injective morphisms and injective morphisms with torsion-free co-curve. Right. So under these hypotheses here, so after the stable rank 2 reflexive sheath of V3, trivial first-term class, and assume that you have. So this space here is the same as home from F to TP3. Under these circumstances, this is the same as home from F to TP3. So assume you have maps from F to the tangent bundle. Then this gives you a condition for the existence of injective morphisms. So this other condition, then there is a monomorphism. So this first one is very nice because every non-zero morphism is injective, is monic. In this other line, so it only guarantees the existence of monomorphism, but it doesn't tell you that every monomorphism, every map is a monomorphism. Right, and then there is other condition. And finally, if you have a monomorphism and you have this inequality here between the dimension of the homes for every possible codimension 1 distribution of degree less than 2, then you have monomorphisms with torsion-free co-curve. So this is so if you have as we did the classification of distributions of lower degree. So once you have the classification of distributions of degree 0 and 1, you can apply this criteria to construct examples of distributions of degree 2. And this technique works in a bunch of other cases. And in some cases, you can do in different ways, right? You can. There are some cases when you can construct examples using all 3 techniques. There are other examples when only one of the techniques work, and so on. What I can tell you is that, coming back to my big scary table here, is that when you are in the lower part of the table, C2 equals 3 and below, we have good control of the stable reflexive sheaves. So stable reflexive sheaves with small second-chain class 3 and below, they are well understood in the sense that there is a bunch of literature that tells you everything you need to know about these sheaves. So for this lower part of the table, it's easier to look at the sheaves and construct the distributions starting from the sheaves. And when the second-chain class is small, the degree becomes large. So curves of large degree, degree 4, degree 5, degree 7, curves of large degree are complicated. So it's hard to deal with these curves, but it's fortunately easy to deal with these sheaves. In the upper part of the table, when the second-chain class is 4 or 5, then the reverse is true. There's not a lot of literature about these sheaves, these reflective sheaves. But the curves are well behaved. And then there's lots of literature about lines and double lines and schemes of degree 2 and so on. So on this upper part of the table here, it's easy to do the construction starting from the curve. Right, you start from the curve to do your construction. And these cases here with second-chain class equals 3 is mixed, right? So you have to actually, it's interesting because you have to actually play with both sides. You use everything you know about the bundles, and you use everything you know about degree 3 schemes to actually show what cases occur and what cases do not occur. It's a fine. You have to do a fine balance between these two worlds, the literature on sheaves, and the literature on space curves. And one example of this tight balance is given by my last slide here regarding non-existence results. So if you take a stable reflexive sheath with these invariants, so second chain class is 4 and the third chain class is L. Remember, as I told you, there's not a lot of literature about these sheaths. And assume, so I do some non-existence results by contradictions, right? So suppose you have a monomorphism with a torsion-free co-kernel. The co-kernel would be the ideal sheath of a double line with this genus, plus a bunch of points. And such lines, the ideal of such lines always has the associated homogeneous ideal associated to these double lines have this form here, where F and G are homogeneous polynomials of degree 5 minus L. L is this parameter here, in the variables x2 and x3. Now, remember, the image of this one form is going to be the ideal of one of these curves plus a bunch of points, right? One of these double lines plus a bunch of points. So the AIs, the coefficients here of the form, they have the degree equals to 3, right? So they are polynomials of degree 3, and they have to be contained in this ideal here, which has this, which have these generators, right? So these generators have degree 6 minus L, right? So when L is small, when L is smaller than 3, the only way that this ideal is contained in this ideal here, right? So these guys of degree 3 cannot appear as multiples of these guys here, right? Because they have degree larger than 3. So the AIs will actually be contained in this ideal. But this is the ideal of degenerate twisted cubic. So it's a degree 3 curve. But my curves are double lines, right? So I cannot have these guys contained there, right? So I cannot have these degenerate twisted cubes contained in my double lines of these higher genus, right? So this gives me the contradiction, omitting a few details. And the final desperate case where, so this eliminates the case where L is smaller than 3. And the final desperate case the last line that I managed to decide on that big table was precisely with these invariants, 4 and 6, when L is equal to 3, 4 and 6. And this was done by, brute force, explicitly finding a one form that degenerates into a double line plus 6 points. And this was done with the help of Alain. So Alain Muniz was the guy that helped me finding this example explicitly, right? So when all the other analytical methods failed, we appealed to brute force, and brute force gave us our last example. So, what I found exciting about this work is really it mixed everything I knew about bundles and space curves, and it was a lot of fun doing populating that big table, because it really helped me learn a lot about these guys. So that's all for today. Thank you very much. And that's it.
Okay, thank you, Marcos. So let's thank Marcos first. Okay, live long is a good motto. Okay, very good. So are there questions?
I have one.
Yes.
Yeah. So about the information you get from the modular spaces, like you were able to calculate the dimension, right?
Yes.
About this, did you get some information about the sheaths from the modular space?
What do you mean, the sheath?
Yeah, the possible sheaths, like from the geometry of the modular scheme.
Well, in this other paper that I mentioned with Alain and Mauricio, we give a more precise description of these modular schemes in certain cases. We know that it has a vibration. We give several more details about this variety, not only the dimension and the fact that it's irreducible. And out of this structure, you can describe certain sheaves, certain bundles on these modular schemes as well.
Okay.
Right? So yes, in some cases we do have more information about these varieties.
More questions? Okay, so I have a question. So first of all, does the singular locus describe the distribution?
No, not in very few cases. Very few cases.
Okay.
In the large part of cases, the answer is no. And in this other paper with Alain, we actually give a very precise answer to that in the case of degree 1, right?
Okay.
So we say that there's actually a projection. So giving some spoiler to Alain's talk, you have a morphism from this modular distributions to the Hilbert scheme. And then we give a description of the fibers.
Okay. Even if you take into account the points.
Even if you take into account the points.
Okay. Okay. And going back to your table, I mean the large table, you mentioned that the curves on the top of the table are very simple, right? Lines or conics.
Yeah.
But the points aren't they more complicated? You have more points.
Yes. Yes. So indeed, so if you look at this second line here, which is the singular scheme is a line and 14 points, this is a very complicated thing, right? 14 points is a lot of points.
Right, right.
And even if you just make a count of parameters, so 14 points, 14 points on P3 gives you what, 50. 42 parameters. 42 parameters.
But you mentioned that they were on a curve, right?
Yeah. So this gives you 42 parameters plus a line, which is another 4 parameters, right? So it would be 46.
Okay.
But the modular scheme cannot have dimension 46, right? So because it's locally closed subscheme of P45.
Okay.
Not all configurations of line and bunch of points do occur.
Right. But when you construct them somehow, I mean, you focus more on the curve than on the points, right? The points come up in a way. I don't know.
Yes. All that I can tell in my construction here is that there are two curves here in this construction. This curve here and that curve. So this diagram gives you a distribution so that the one-dimensional part is given by this curve here that appears in this bit of the diagram, and the point will belong to this curve here.
Right.
So this is some, like in this example here. So my 14 points are not any 14 points, but they are contained in this curve of degree such and such and d. So this gives you some restriction on what kind of points can arise. Right? Yeah.
And there's one more question. Do you know the relation between the strata? I mean, could it be that one stratum is in the closure of another one, or somehow?
Yes.
Like closure in the projective space of the forms, right?
Yes. So yeah, each strata is a locally closed subset of a P large, right? And these strata may intersect one another, and one strata may lie completely in the closure of the other. This can occur. It doesn't occur in the degree 1 case, I think, if my memory doesn't betray me, but it does not occur in the degree 1 case, but in general, it may occur.
Okay, okay. Very good. Okay, are there more questions? Oh, yes. Okay, so if not, let's thank Marcos again. Very well, so I will stop recording.
Obrigado, Marcos.
Diga, Ethan.
Ethan, do you have a question?
No, I just said thank you. Sorry.